Works.
Okay, so we are ready for the next speaker, Romain Ruzziconi from Oxford, talking about Carrollian amplitudes from holographic correlators.
Thank you. So first, I would like to thank the organizer for giving me this great opportunity to talk about my research. So in this presentation, I will discuss the Carrollian amplitudes and their relations with the holographic correlators in ADS. So this presentation will be based on two papers which have been done in collaboration with Lionel Mason, Akshay Yedeshpo-Srikan, Fernando Alde, and Marianucci. So the question I would like to ask in this talk is how to formulate flat space holography. And by that I mean a correspondence between gravity in asymptotically flat space-time. And for the purpose of this talk, I will essentially focus on the four-dimensional case and a lower dimensional field theory without gravity. So in this talk, I will focus on a bottom-up approach to holography, which means that I will try to deduce some aspects of a putative dual theory at the boundary, starting from what we know in the bulk of the space-time. And as we saw in the previous talk, there are two proposals that have been discussed in the literature. The first one is called celestial holography. And in that case, the putative dual theory to 4D flat space will be a two-dimensional CFT living on the celestial sphere. But there is another proposal which has been discussed more or less in the same years, which is called Carrollian holography. And in that case, the dual theory to 4D flat space will be a three-dimensional Carrollian CFT living at null infinity, so at scri plus and scri minus. So here are the takeaway messages from this talk. The first is that even if these two proposals for flat space holography look completely different, just even by the dimension of the putative dual theory, we have shown that they are actually equivalent, which means that in principle you are free to choose either of these approaches. So in this talk, I will mainly focus on this Carrollian holography proposal, and I will show that you can encode the bulk S matrix in flat space in terms of boundary Carrollian CFT correlators, and I will call these correlators Carrollian amplitudes. And then I will show that these Carrollian amplitudes are actually the natural object obtained from the flat limit of the holographic correlators in ADS. And of course, the ultimate goal of this program is to deduce flat space holography from a flat limit of the ADS CFT correspondence. So to make sure that we are all on the same page, let me just remind you about this Carrollian limit. So this refers to this ultra-relativistic limit that was considered by Lévy-Leblanc in '65, and that consists in taking the speed of light, c going to 0. So this is the opposite of maybe the more standard Galilean limit, where you take c going to infinity. And if you implement this Carrollian limit at the level of the Poincaré algebra, this corresponds to an Inonu-Wigner contraction, and what you get in the limit is the Carrollian algebra. You can also implement this limit at the level of the conformal symmetries, which are given by SOD, 2 in Lorentzian signature in d dimensions. And in that context, you will get the global conformal Carrollian algebra. So now what is the relation between this Carrollian limit and null infinity? Well, let me give you a simple example here. So you can start with this Minkowski metric, where you just restore the dependence in the speed of light. And if you take c going to 0, what will happen is that the metric will become degenerate in the limit. So it has no leg in the time direction. The problem is that you cannot invert this metric on the space-time, which means that you also need to consider the Carrollian limit of the inverse metric. And in that case, you will get a vector field, n, which has only legs in the time direction, and which will be in the kernel of this metric. So that allows me to define more generally what I mean by a Carrollian geometry. So that will be the data of this degenerate metric, QAB, and a vector field n, which is in the kernel of the metric. So now what is the relation with null infinity? Well, remember that scry is a null hypersurface, which means that the metric which will be induced there will be degenerate. And indeed, you can show that if you do the conformal compactification in asymptotically flat spacetime, you recover exactly this Carrollian geometry at the boundary. So now in that context, you can reinterpret the BMS symmetries, which are the asymptotic symmetries in flat space, as the conformal symmetries for this Carrollian structure at non-infinity. So they will preserve this degenerate metric and this vector field up to some rescaling. So now this allows me to state this important isomorphism between the BMS symmetries in d+1 dimension of bulk and the conformal Carrollian symmetries defined intrinsically on the d-dimensional boundary. So as I said before, this Carrollian holography proposal suggests that the dual field theory is living at scry. And just by a matching of the symmetry, this theory should be a Carrollian CFT, which means that it exhibits the conformal Carrollian symmetries, or the BMS symmetries, as global spacetime symmetries. So examples of Carrollian CFT have been built in the literature by just taking the Carrollian limit of standard Lorentzian CFT. Let me also say that this Carrollian holography proposal follows a similar pattern than the IDS CFT correspondence, because it's a codimension 1 holography. And as I will argue later, you can take a flat limit in the bulk of IDS, and this will implement this Carrollian limit at the boundary, which means that you can, in principle, start with a holographic CFT in IDS and get this Carrollian CFT living at the boundary of flat space. But first, the question that I will ask here is, can we encode the bulk S matrix into boundary Carrollian CFT correlators? So to do that, I will work with the so-called boundary coordinates, which are particularly well adapted if you want to approach null infinity. And these are given by these coordinates here. So you have this U coordinate, which is just a null time along the boundary. R is a coordinate that allows you to approach scry plus and scry minus by taking either R to plus infinity or R to minus infinity. And then you have these Z and Z bar coordinates here, which are just the coordinates on the celestial sphere. So the boundary coordinates are related to the standard Cartesian coordinates in this way, and you can write the Minkowski metric in this form. So it's a very simple expression. And what you can do is to push this metric at the boundary, and what you will get is exactly this Carrollian structure that I was mentioning, with a 0 here in front of the du square. And now the Carrollian vector field is just this du vector along the boundary. So now the BMS symmetries will be the conformal symmetries for this Carrollian structure, and they will be parameterized by two types of functions. You have the supertranslation parameters here, which will depend on Z and Z bar. And there are also the superrotation parameter, which satisfy the conformal Kidney equations in 2 dimensions, and they will generate the conformal transformations on the celestial sphere. So now one more definition before stating the dictionary. So I will need a notion of conformal Carrollian primary, which is the analog of a primary in the standard CFT. So it will be an object that will be living at scry. It will depend on U, Z, and Z bar. And I will require that it transforms in the following way under the action of the BMS symmetries. And you see that this transformation laws involves some weights, K and K bar, which are called the Carrollian weights. And these are in some sense the analog of the conformal weights in a 2D CFT. So the kind of correlators I'm interested in are these boundary correlators involving these Carrollian primary. So what is the relation with the bulk? Here the strategy will be to start from a spin S massless field in flat space, and S here can be taken to be 0, 1, or 2, so scalars, gluons, or gravitons, and I will push this field at the boundary, at scry. And basically, this first entry of the dictionary will be to identify this boundary value of the bulk field with my Carrollian operator that I've just defined here. And you can show that this identification actually fixes completely what the Carrollian weights are in this transformation law. So they will be completely fixed in terms of the helicity of the bulk field. Epsilon here is just +1 or -1, so it tells you if the operator is outgoing or incoming, so it's inserted as scry plus or scry minus. So now you can consider this endpoint massless scattering amplitude in flat space, and it's usually expressed in momentum space, so it will depend on the momenta of the particles involved in the scattering. And since these are massless particles, you can parameterize this momentum with the energy of the particle, omega, and W bar, the directions on the celestial sphere. So now what you can always do is to start from this scattering amplitude in momentum space and perform a Fourier transform with respect to the energy of the particles, so with respect to omega. And what you get at the end is an object which is living in position space at scry, so it depends only on u, z, and z bar. And the holographic input here will be to identify this object with a correlator of Carrollian primaries. So that's why I will call these amplitudes in position space at the boundary Carrollian amplitudes. So this dictionary also ensures that you can compute the correlator in the bulk theory and push them at the boundary with an appropriate rescaling and obtain these Carrollian correlators at the boundary. It's a kind of extrapolate dictionary. So now you can show that this identification actually makes sense. So the Carrollian amplitude will satisfy some Carrollian CFT word identities, which are displayed here. And it works a bit like in a standard CFT, where the low point correlation functions will be fixed by the symmetries, and the higher point function will give you some non-trivial information about the dynamics of the theory. And there is already something interesting happening for the 2-point function. So if you try to solve the word identities, these Carrollian word identities, you will find that there are 2 branches of solution. One which is called the electric branch, and which will be dependent on u, so this null time at scry, and it will involve this delta function with respect to the angles on the celestial sphere. But there is another branch which is u independent, and it actually corresponds to a correlator of a CFT living in 1 dimension lower, so namely a 2D CFT. So as I will explain later, this is the electric branch which will be relevant for the massless scattering in flat space. Before doing that, let me make technical comments. So here, if you consider a Carrollian primary, and that you take some du derivative on it, you can show that you obtain another Carrollian primary. So this object here will transform exactly in the way I prescribed before here, except that the weights k and k bar in the transformation will be shifted, so depending on the number of derivatives you are taking. So this means that I can also consider these correlators of du descendants that will also satisfy the Carrollian CFT word identities. So that will be useful for us in the following. So now let me give you some simple examples of Carrollian amplitude, and I will start with the 2-point function, which is the simplest example, and it's here expressed in momentum space, so it will depend on omega, the energy of the particles involved in the scattering. And if you perform the 2 Fourier transform, as I prescribed before, you can re-express this object in position space at scry. So this is what you get, and M1 and M2 count the number of derivatives you are taking on the Carrollian primaries. So if you compare this object with the solutions of the Carrollian word identities, you see that it corresponds exactly to this electric branch. So this means that the Carrollian CFT that will anchor the massless scattering in flat space will be an electric Carrollian CFT. So now a more complicated example, but still quite simple, is the 4-point contact diagram for a massless scattering for a massless field. So this is just a delta function, a momentum conserving delta function. And what you can do is to perform the Fourier integrals by considering the following parametrization of the delta function. And what you find at the end is this expression here, so which depends only on u, z, and z bar. And an important fact about this expression is that it's still distributional, so it will involve this delta function in z and z bar, which are the two-dimensional cross ratio on the celestial sphere. So they are defined here. So this delta function will be important for us when looking at the flat space limit. Let me say that we also have similar results for the 4-point exchange diagrams, as well as for the n-point gluon and graviton MHD amplitudes in flat space. So we have a lot of examples for these Carrollian amplitudes, at least at 3 level. So now I would like to argue that these Carrollian amplitudes that I've defined in flat space are the natural object obtained from the holographic correlators in ADS by taking the flat space limit. So these holographic correlators are CFT correlators living at the boundary of ADS, and they can be computed via the ADS Witten diagrams in the bulk. So here, to take the flat space limit, I will work in these boundary coordinates, which also exist in ADS. So they slightly differ from the Minkowski metric by this term, which involves S, L, this ADS radius. So these boundary coordinates are covering 2 Poincaré patches. One will be with R, positive R value, and the other with negative values. So you can relate these boundary coordinates in ADS with the more standard, maybe Poincaré coordinates in the following way by performing this transformation. So now let me make a simple observation. If you take the flat space limit on this ADS metric, ADS4 metric, this term will just disappear in the limit, and you will recover the Minkowski metric, which means that the boundary coordinates have the nice feature to admit a well-defined flat limit, which is not the case if you are working, for instance, with these Poincaré coordinates and that you take naively L to infinity. So another thing that you can do is to push this metric at the boundary and get this Lorentzian metric at the boundary of ADS4. And then if you implement the flat space limit, you will recover this degenerate metric living at the boundary of flat space, and which is part of the Carrollian structure. So by this naive observation, we see that the flat limit in the bulk of ADS, so taking L to infinity, implies a Carrollian limit at the boundary, which amounts to take this C going to 0 limit. And what you can show is that this naive observation also extends for metric, which satisfy Einstein's equation and which are asymptotically ADS. So you can also implement the flat space limit in boundary gauge. This has been done in this paper. And recover the asymptotically flat space solution and reinterpret the equation at the boundary as Carrollian evolution equations. So now the question I would like to ask here is, does this correspondence between flat limit and Carrollian limit work at the level of the amplitudes? So the strategy here will be first to implement the flat space limit at the level of the ADS Witten diagrams. And then I will also study separately the Carrollian limit at the level of the boundary correlators and show that they will reproduce the Carrollian amplitudes. So the building blocks of these ADS Witten diagrams are these propagators in ADS. So first you have the bulk to bulk propagator, which for a massive scalar field in ADS4, which satisfy this Klein-Gordon equation with the source term here. And if you express this box operator in boundary coordinates, it will take this form. And again, you can take L to infinity, and you can show that this box operator indeed reduces to the box operator in flat space. So now the mass term here can be expressed in terms of delta, the conformal dimension, and L square. And again, if you take L to infinity, the mass will completely disappear in the limit, which means that you start with a massive scalar field in ADS, and following this prescription, you will end up with a massless scalar field in flat space. So in particular, the equation here that you get in the limit will be solved by the Feynman propagator in flat space. And what you can show is that this limit also works directly at the level of the expression themselves. So you can take the flat limit of the bulk-to-bulk propagator and get this Feynman propagator in the limit. And in particular, the information about delta completely disappears in the limit. So you can do something very similar at the level of the bulk to boundary propagator by just taking, so these are obtained by just taking R to infinity. And if you take the flat limit on these, what you can show is that you will get the bulk to boundary propagator in flat space up to some du derivative acting on it. So here the information about delta, the conformal dimension, is not completely lost. It will be encoded in the number of derivatives that you are taking on this bulk to boundary propagator in flat space. So here I'm discussing this limit at the level of the outgoing propagators, but you can also do the similar discussion at the level of the incoming propagator. And that allows me to present this general picture of the flat limit that we are taking. So we have two Poincaré patches, and basically one of the Poincaré patch, at least the boundary of this patch, will be matched on scri plus, and the other will be matched on scri minus, which means that we have a notion of incoming and outgoing through this flat limit procedure. So this square here just summarizes what I say, and now I would like to implement the flat space limits directly at the level of the ADS Witten diagrams. And to do that, so I will start with this 4-point contact diagram, which is just a product of bulk to boundary propagator in ADS, which is integrated over the bulk. And here, if you take the flat limit in boundary gauge, as I explained before, each bulk to boundary propagator reduced to the one of flat space up to these m counting the number of derivatives that you are taking. And you can show that this expression here, in the right, is the expression for the Feynman diagrams in flat space for this Carrollian amplitude. Okay? So it means that just by taking the flat limit in boundary coordinates, we show that the ADS Witten diagram reduces consistently to the Feynman rules in the flat limit. So now the question is, can you implement the Carrollian limit directly at the level of the holographic correlators without referring to the bulk? Okay, and recover this expression of Carrollian correlators. So that's what I'm going to do now. And I will start with the simplest example of the 2-point function. So this can be, for instance, obtained from, so you want to compute the Lorentzian 2-point function, which can be obtained from the Euclidean one by analytic continuation, or directly from the bulk to boundary propagator by pushing the other point to infinity. And this gives you this expression in boundary coordinates. And again, I will identify here, so it's a formal identification between the speed of light at the boundary and this ADS radius in the bulk. So this is my starting point. It's a Lorentzian 2-point function in the CFT, where you have the explicit dependence in the speed of light. And if you take C going to 0, what will happen is that you will get two branches of solution in the expansion in C. So they appear at different order in C. The first branch will not depend on U, so this is just the branch obtained by taking C going to 0 here. This is the naive result that you will get. And this corresponds to the magnetic branch of, for the Carrollian ward identities. So now there is another branch which is more subtle and that arises on this, on the support of the delta function. And this corresponds actually to the electric branch of the Carrollian ward identities. And you can show that for the weights of interest, this is actually the leading term. So it means that if you rescale the conformal primary operator, you can just reproduce the 2-point function, the Carrollian 2-point function, by taking the Carrollian limit of the Lorentzian CFT 2-point function. So now a more complicated example at the level of the 4-point contact diagram. So as I said before, it can be computed with this integral in ADS, and that can be reduced to this D function in ADS. So there are functions of the cross ratio here, U and V, and they will also depend on the delta, which are the conformal dimensions of the external operator inserted at the boundary. So an example of D function is given here. If you take all the deltas to be 1, this can be expressed in terms of log and dilog functions if you express these U and V variables in terms of this complex Z variable. So this is computed in Euclidean signature. So the first step is to go to Lorentzian signature. And to do that, you have to do an analytic continuation. And there is a very subtle story there. So you can show, for example, if you take all the deltas to be 1, that this analytic continuation will lead to these singular terms in Z minus Z bar. And these singularities arising in the analytic continuation will be called the bulk point singularities. So they will be extremely important for us in the flat space limit, and in particular, the leading singularity will be relevant. So for the example that I gave here, this is just given by this term. Okay, so now importance observation, and then I will conclude. So you can express this Z minus Z bar here, which captures information about the singularity in terms of boundary coordinates. And what you will find is that at the 0 order in C, this corresponds to Z minus Z bar, so the difference between the cross ratio on the celestial sphere. And then you have correction terms in C square. So it means that on the support of Z equal to Z bar, taking the Carrollian limit implies isolating the bulk point singularity. So you see the bulk point singularity emerging from the Carrollian limit. And you can start with this leading singularity that I was mentioning before, and this will reproduce this delta function with respect to the cross ratio, which is something that we had in the 4-point function in flat space. And now you can compute explicitly this coefficient in front of it and find this explicit expression. And this term here, this denominator, corresponds to the expression that we had for the 4-point Carrollian amplitude. Now putting everything together, you can take the Carrollian limit of this full 4-point function, and you can rescale the primaries in the same way that we did it for the 2-point function, and you can reproduce this 4-point Carrollian amplitude. So this matches perfectly with all the factors. So let me just say that this can be reproduced for the exchange diagram as well. Okay, so now the conclusion. So here I tried to convince you that the Carrollian approach to flat space holography was useful, especially if you were interested by the connection with ADS-CFT correspondence. And we have seen that the Carrollian amplitudes that encode the bulk S matrix can be obtained from the flat space limit of these holographic correlators in ADS. And so now the question is, how far can we go? Can we use this flat slash Carrollian limit of ADS-CFT to deduce some top-down model for Carrollian holography? So that's something that I'm investigating right now. Okay, thank you very much for your attention.
Questions?
This is just a comment about this last part about the delta functions. It's a lot more straightforward if you do it directly in momentum space, if you forget this form. Because you have a very complicated expression. You wrote the delta function after you express it in the Carrollian variables, and it was kind of these 2 lines. If you do the direct computation directly in momentum space, you will automatically get the momentum preserving delta function.
But if you do it in momentum space, can you also see this Carrollian limit at the boundary? Because this was basically the point of this way of taking the limit, is that we want to see this flat space limit as implementing a Carrollian limit at the boundary. And okay, in momentum space maybe it can be done, but
from the ADS-CFT perspective, because at the very end you were doing as a flat space limit of ADS-CFT, and then I would say for that perspective, doing it directly in momentum space.
Right.
It's a lot more straightforward, and also the formulas work much, in a sense, the contact diagram that you spent 2 slides is 2 lines in that context.
Right. So here the point is that we want to take the Carrollian limit at the level of the dual theory. So if we have an explicit example of duality in ADS-CFT, then the hope is, for example, to start with n equal 4 superior mills and implement the Carrollian limit. So that's why we were really following all the steps, at least in position
that
space.
Also in momentum space.
It's a good question. Yeah, thank you.
This may be overly complicated, but could you repeat the same limiting procedure for other asymptotically ADS spacetime, a black hole?
So what I can say is that we looked at these metrics which solve Einstein's equation and which are asymptotically ADS. So at the classical level, it works perfectly. You can work, so this was this comment here, so this is discussed in this reference. You can work in Bondi gauge, take the flat limit, and recover the metric which are asymptotically flat. So there are subtleties if you want to capture the radiation, for example, in the flat limit, concerning the boundary conditions, but this has been done very explicitly.
So this is probably a really dumb question, but to what extent is this a one-way street? So in some cases you know lots more in the Carrollian setting than you do in ADS. For instance, you have endpoint functions, say in the MHV sector. Could this tell you anything about what something like a Park-Taylor formula in ADS is supposed to look like?
So here the philosophy was to try to understand this correspondence between flat space limit and Carrollian limit at the boundary to apply it to exact holographic dualities in ADS. That was the. So I don't know if you can go the other way around and deduce some correction with respect to the flat limit. That's not of use to me because a priori you can start with different CFT and obtain the same Carrollian CFT in the limit. So a priori there is some ambiguity there by going on the other way.
Carlos, and then this is the last question.
Thank you. So I think this question was asked in different ways, but let me ask it this way. So in the diagram you have, suppose that you start with n equals 4 super Young mills, right? And we write the Lagrangian. What do I have to do to get a Lagrangian that will produce the Carrollian amplitudes?
Right. So there is an example that has already been worked out, which is the ABGM model. So you can start with this Lagrangian and implement the Carrollian limit. So usually what you find is that there are two branches of Carrollian theory that arise in the limit. There is a magnetic branch and an electric branch. So what you will have to do is to isolate this electric branch, which is the one relevant for the scattering. And in principle, computing the correlator in this Carrollian version of n equal 4 super Young mills or ABGM might be able to tell you something about the Carrollian amplitudes in flat space. Of course, there is a subtlety of what is happening in the flat limit in the bulk. For example, if you take ADS5 process 5, what is happening with the S5? That's a good question, but this is the philosophy.
Correlators are not charged under the RC.
Right, at least at this stage.
Okay, I think there were more questions, but we don't have time, so let's break for coffee and reconvene at 11.